Good morning, student. So today we want to look at how to tell if the limit failed to exist. So how can you tell that the limit has failed to exist? We have already made such an example. Remember with the Heaviside function that we had previously in our previous video. So we found from the Heaviside that the limit st approach 0 from the left of the Heaviside function. Remember we found that to be 0, which was completely different from the limit st approached 0 from the right, which you can remember that we got it to be 1. So this was one of the part where we could conclude at that time that the limit st approach 0 of h of t does not exist. So does not exist. So this is the first case that we got previously. But today we want to look at in other cases where the limit also fails to exist. Here we conclude that once the two-sided limit, the left and the right, are different, then we can conclude that the limit does not exist as t approach that point that we are interested in. So let's now look at this example where we have a sine of pi over x, and then we want to test the limit as x goes to 0. And one thing to pick from this function is that the function is undefined at x is equal to 0, but that should not be a point, should not be a problem, because we are interested in the values of x which are as close as possible to 0, but not when x is equal to 0. So let's start with some values here. So let's let x to be 1 and then evaluate f of 1, then you get to be 0. Then make it smaller as we approach 0. Now take half and then evaluate f of half, you get 0 again. Make it even smaller than half by dividing by 3, then you still get 0. You make it smaller to show that you want to approach 0. As the value of x gets smaller, f of x here in this case remains 0. And then take 1 over 10. You can see you are skipping some numbers between. So let's take 1 over 10 and see. If you take 1 over 10, f of x, which is just sine, it becomes 0 again. And then you take 1 over 100, f of x becomes 0. You try to take a very smaller, very close to 0, 0.0001, you still get 0. Interesting. We are likely to make a wrong guess here with this value. We are tempted to guess that the limit as x approaches 0 of f of x is nothing but 0. But that is very wrong. That's a wrong guess from the few counterpoints that we picked. In fact, it's just that we picked points that could agree with what we wanted to portray. And we took points which are a little bit far from each other. Suppose somebody takes other points 2 over 5. And then you plug it as x, you'll find that f of x is equal to 1. Even when you take 2 over 101, you will find that f of x is still 1. In fact, try 2 over 2n minus 1, where n, let it to be, for simplicity, let n to be just an integer. So try that. Try as many as possible. You find that you will not get 0. So that's one thing. So, and make it n to be as large as possible to show that you want to approach 0. Then you'll find that you'll not get 0. So one thing which we notice as we plot the function, this function, is that as we get close and closer to 0 with the values of x, you find that the behavior of the function oscillates between -1 and 1. And because the function is oscillating between -1 and 1, there is no a fixed point that we can say we are approaching. Every time we change value, the function jumps and keeps oscillating between the 2 points. So in this case, we will say the limit does not exist. So we are saying the behavior of the function as x approaches 0 is oscillating infinitely as many as possible as x approaches 0, is oscillating between -1 and 1. Therefore, we conclude that the limit does not exist. This is another case where we can say the limit does not exist. Bear that in mind as we go along. So now we want to talk about infinite limits. Let's introduce infinite limit, and then as we introduce infinite limit, we'll also talk about vertical asymptotes. So we can define a new concept here, that the limit of f of x is infinity as x goes to a, meaning the values of f can be made arbitrarily large by taking the values of a which are very close, the values of x which are very close to a. So that's the point. But we are not taking the when x is equal to a. Or in another words, we can say f of x becomes very large as x goes to a. Then we'll use this sign, which is an infinity. So the symbol, this one, be careful, is not a number, but the expression, this one, the limit of f of x is infinity as x goes to a, can also be read as the limit of f of x as x goes to a is infinity. Or another person can say f of x becomes infinite as x approaches a. And take the word infinite, it means it gets large. And or another person can say f of x increases without bound, is not bounded as x goes to a. So those are some of the way to put it in a simpler term. So remember, infinite is not a number. It's just to denote that the limit of this function gets large and large as x goes to a. We can represent the same idea with a graph where we can approach this a from the left, and then as we get closer and closer to a, you can see the values of the function get large and large. Even when you try from the right, you start from far and then you get closer and closer and closer to a, you can see the value of the function on the graph are increasing. They get large and large, so we can say the limit, and they become positively large. So the limit of f of x is infinity as x goes to a. That's the conclusion we can make from here. You can also look at it when as x goes to a, in this case, you can see that they become negatively large. So they become negatively large as we get. Look at even when you start from the right, start somewhere far, here's the value of f of x, and then you get closer, you get the value of x, you can see it's becoming negatively large. As we get close and close, it becomes more negative or negatively large. So we'll say these functions become large negative as x gets closer to a, or the limit of f of x is negative infinity as x goes to a. That is the notation that we are going to use for infinite limits. We can give this definition to say, let f of x be defined on both sides of a, then we don't mind what happens at x is equal to a. What we are saying is that the limit of f of x is minus infinity as x goes to an a, which means the values of f of x can be made arbitrarily large negative by taking values of x which are very close to a. We don't need to reach to a. And the simple, this one can also be read as the limit of f of x as x approaches a is negative infinity. And one example is this function that is given here at the bottom, which is a very beautiful function. You can see that in the denominator you have x squared. So it means whether you substitute a negative number or a positive number, what results from x squared is positive. So the negative that will count is this one, which will take our values to negative. And you can see we are dividing by small values which are close to 0. As they get closer and closer to 0, the function blow up to minus infinity. So the values of this function becomes negatively large, which is why we have negative infinity. So we can talk about this using one-sided limit like previously we did. So if we approach from the left, then you get the limit to be infinity. Also, if we approach from the right, you also get the limit to be infinity. We can denote it like this. Even when you approach from the left, you get minus infinity. This is how we will denote it. Even when you approach from the right and then you get minus infinity, this is our notation, which means that as x goes to a from the left, we consider, remember, we consider only values that are less than a. And similarly, with as x approaches a from the right, we consider only values of x which are greater than a, remember, in this case. But be careful of these one-sided limits, that they still apply with infinity, that the limit of f of x is infinity as x approaches a from the left. And also it can be positive infinity as x approaches a from the right, or the limit of f of x can be negative infinity as x approaches a from the left, or it can be negative infinity as x approaches a from the right. Those are all possible cases that we can have. And we can also look at them from the graph. So in the first graph, you can see that here you have your graph on the left of a. So the only possibility that you have here is to approach a from the left. So you can get closer and closer and closer to a and see the values of x go to positive infinity. So we can say the limit of f of x is infinity as x goes to a. And on this number b, you can see that you have only a graph on the right of a. So it means we can approach a from the right. That means we can get closer and closer to a. And as we do that, you can see the values of the function go to infinity, positive infinity. Therefore, we can say the limit of f of x as x goes to a from the right is positive infinity. On the number c, you can see that as we get closer to a from the left, the values of the function get negatively large. So we can say the limit of f of x as x approaches a from the left is negative. The same thing with the last option. You can see that you can only approach from the right, but even though you're approaching from the right, the function, as we get closer and closer to a, the function goes to minus infinity. These are some of the cases that you will meet as we go along, but take care of this and be able to deduce something from the graph. So, what is our take? we want to introduce the vertical line. So a line x which is equal to that it becomes a vertical asymptote if at least one of the following statements are true or is true. One of them. If it's true, one of them, you could have the limit of f of x being infinity as x goes to 0, or you could have the one-sided when you approach from the left being infinity, and also when you approach from the right being infinity, or the negative of all of them. So once you have one of these cases, know that the line x is equal to a is a vertical asymptote. That is the definition that we give now. So once we have one of these cases, know that you have x which is equal to a as a vertical asymptote. Look at this function that we have here. Suppose you ask a question to find vertical asymptotes of f of x which is equal to tan of x. The best way in this case is to approach this function to find the vertical asymptote. We know that as the denominator approaches 0, this function will blow up towards minus infinity or plus infinity. We have seen that when you are dividing by something that is very, very small, which goes to 0, then the function blows to plus or minus infinity. So that's why we want to consider in the neighborhood of the function cos of x, which is equal to 0, to see what happens. So suppose, as you know from algebra, I remember some of you, we were able to have a graph of cosine and sine. So let's say we have 0, you have pi over 2, and then you have pi. Let me just stop here. You can go as far as you want. You know, it's a repeating function, so it's a periodic function which will keep repeating. But let's stop here, just for this example. You can have minus pi over 2. You can have minus pi. So you know that for cosine, here let's say you have 1, and then somewhere here you have minus 1. So you know for cosine, it takes at 0, it will take at pi over 2, at minus pi over 2 it will take 0, and then when you get to 1 it will take the maximum, which is 1 at x which is equal to 0, and then it goes back at pi over 2, it gets to 0, and then at pi it gets to the minimum, which is minus pi, which is minus 1. The same thing on the left. If you extend this portion, and then you find that the cosine becomes minus 1 when you get to minus pi, but at pi over 2 it becomes 0. That's one beautiful thing that we see here. So look at from the graph. Let's say you approach pi over 2 from the left. So you start somewhere here, and then you get closer and closer to pi over 2. Look at the graph. The graph goes to 0. So, but it goes to 0. The values of the function there, they are positive. So we can say cosine goes to 0 from the positive as x goes to pi over 2. And also look at as we approach from the left. As we approach from the right, not from the left. Look at as we approach from the right. If we start somewhere here, and then we get closer, and then get closer, be careful that although the values of f of x approach 0, but they are negative. You get closer, they're still negative, but they approach 0. You get closer, they're still negative. So as x approaches 0 from the left, the function cosine approaches 0 from as x approaches 0 from the right, the function as x approaches 0 from the right, the function cosine of x approaches 0 from the left. That's what we are seeing, because it gets towards 0 but with negative values. That's one thing. And look at the sign. The sign function on that interval, if we start from 0, remember sign, it will start from 0. If we look at just this portion, at pi over 2 it reaches maximum of 1, and then it goes back to 0 at pi. So you can also extend it on the left, no problem. But the interest is around pi over 2. Look at the sign of x remains positive throughout that neighborhood of pi of x, which is equal to pi over 2. So what is controlling the sign here is the denominator, cos of x, around that neighborhood of x, which is equal to pi over 2. So that means if cos of x is positive, then tan of x will be positive in the neighborhood of pi over 2. And also if cos of x is negative in the neighborhood of x, which is equal to pi over 2, tan will also be negative. So that's why we can conclude that in that neighborhood, when x approaches pi over 2 from the left, which we have seen that cosine is positive, then we get very, very large but positive values. And also as x approaches pi over 2 from the right, from this statement we can conclude that tan also gets negatively large, but because x approaches pi over 2 from the left. These are the two conclusions that we can make. So this portion can help us to deduce this part, and then this last part can help us to deduce this one, because we have agreed that the controlling part is the denominator, which is cos of x. When cos of x, it becomes positive, but remember now cos of x goes to 0. So since we are getting closer to 0, this function will become positively large, but we are approaching 0 from the positive part of cosine. And then also here we are approaching 0 from the negative side of cosine. Since we are dividing by the negative number, but which is going to 0, then we get the negative results of tan. That's what we have. So for this part, since we have just described the previous one a lot, so you can take the previous part and then conclude this one. In fact, this is a graph of at y which is equal to tan theta. So one thing which you can pick from y which is equal to tan theta, remember you can write that as sine x over cos x. So that means tan theta, wherever cos of x is 0, it will have some vertical asymptote. So that's why we have at 3 pi over 2, that's where cosine is 0. We have one asymptote. At pi over 2, that's where cosine is 0. We have another asymptote. At minus pi over 2, that's where cosine of x is 0. At x which is equal to minus 3 pi over 2, that's where cosine of x is 0. We have another asymptote. As many as possible, this is just a small portion that is shown here. So you can see that as take for example the one that we did previously, pi over 2. Let's focus on this point, pi over 2, and check on the neighborhood of pi over 2. You can see if we approach pi over 2 from the left, the values of tan becomes positively large, but if we approach from the right, they become negatively large. So that's the conclusion that we made previously. So you can revisit that from this example. I think we stop here with this lecture. So next time we are going to meet as we evaluate limits. So we are going to evaluate limits next time. So we are going to either use the direct method to substitute into the limit. I think now we have built up a concept of limit that most of you now can be able to get the limit either using the table or the graph. So next time we'll use direct substitution. So let's meet next week. This is the last video of this week. Otherwise we'll meet in the chat room on Friday to to get your questions and try to address some of them wherever possible. So let's meet next week, continuing limits. Probably we'll finish them next week.